All right, guys, I wanted to go over an activity 3 question that I feel like sometimes trips people up, but it really hits home the concept that we were talking about in terms of exact versus estimated percentiles, what assumptions we make about them, and when we would want to use them. So the first one that I want to go over with you is the exact percentile, because I feel like for the most part, you guys have that one down pretty well. And then the first thing we need to know before we start doing this is we need to know our mean, our standard deviation, and then the raw score of interest. Okay, so in terms of that, our mean is given to us 949. Our standard deviation is 173. And our raw score of interest is 801. So all of these were given to you in the activity. And from here, I think the best course of action is to create a distribution and take a look at some of the characteristics that we might have going on here. Okay, so usually when we draw our bell curve, it looks fairly normal in terms of shape. You could, make a frequency distribution with your data and see if there are any funny looking characteristics, but generally I just draw the same shape every time. So when we set up our distribution, we know the center is 0. Oh, sorry. I wanted to write that somewhere else. We know that the center is 0, so that's where our mean exists. So in this case, our mean would be 949. And then we can go above that mean a certain number of standard deviations. So this would just mean 949. If we go to 1 standard deviation above the mean, we add 173. So we would get 1123. Add 173 to that. We get 1249. Add 173 to that. Oh, sorry. We don't get 1249. I misread. 1296. That's what it is. Add 173 to that and you get 1470. Okay, similar things if we go below the mean. We have -1, -2, and -3 standard deviations. So we would start at the mean and we would subtract 173. So we have 776, 602, and 429. Right? And so within this distribution, we can ask ourselves, where does 801 exist? Now in Excel, maybe you used a count if function, since I gave you kind of this block of data, right? And you could say, I want Excel to count how many values are less than or equal to 801 in this given distribution. And then you divide that value by your total sample size, and then you get your percentile, right? That's how we calculate exact percentiles in samples. With the distribution, you can pretty easily kind of guesstimate, right, without actually calculating it, just visually. You can guesstimate where 801 would lie just based on the number line on our x-axis. So 801 is going to lie between 776 and 949. So we can just draw a line and say that 801 lies here, okay? And we would expect that the percentile is representing this area under the curve, right? Also including around these numbers. I just don't want to scratch through them. Okay, and so with this information, if you did the countif function, right, you should have seen that the percentile at which 801 lies at, right, is 21.32%. Okay. And actually, I'm going to do that in a different color so we can point out some differences. So percentile is 23 point, just kidding, 21.32. Oh boy. Okay, so that's good, right? I feel like most of you pretty much understand this concept so far, right? And then there's a question that says, what is the estimated percentile, right? So different method, right? Exact percentile is specific to the sample we're working with, regardless of what the shape of that distribution looks like. Estimated percentile, however, which I'm gonna move this up, as if we're looking at an estimated percentile, you guys will remember that estimated percentiles have to meet the assumption that the distribution is normal, right? And this is because we use z-scores, right? So I'll put in our z-scores here. And z-scores, we know the negative table gives us percentages from, or percentiles, probabilities, right, from 0 to 50%. And then the positive z-score table gives us 50% to 100%. So just based off of that information, we could create a distribution. Oops, that does not look normal. We could create a distribution with all of the values that we had in, our beginning exact percentile graph, but instead I'm just going to put our z-score equivalents, which are the same as our standard deviations in the above graph. So similarly, we're still looking for where x, or what the percentile at x equals 801. And we know that based on the units we're working with, it should still be between -0 and 0 standard deviations, right, which is where it was located in the first graph that we made, or the first curve. Okay, so similarly to the first curve, we're still wanting to see what the probability is that a score will land at or lower than, right, 801 in our distribution. And so if we're using an estimated approach, that means we have to calculate the z-score, right? Z-score is x, so 801, minus the mean, 949, divided by the standard deviation, which we said was 173. Okay, you should get something between -1 and 0, which will point you to the negative z table. And when we look up our information on that negative z table, you should get a percentile, right, for this shaded area, a percentile that reads 19.77%, or 0.1977, right? And so then some of you might be thinking, well, I have to answer this question on why the percentiles are different, right? Because we have this discrepancy here, if I zoom out, of an exact percentile of 21.33% and a percentile of 19.77. So why are they different, right? And this difference in percentages kind of points to one of the key aspects that I have been trying to hit home with this, is that when you have an estimated percentile, you have to assume it's normally distributed. So what does this mean with regards to our distribution? It means if you remember the ranges of our percentages in our z tables, we assume 50% of the data is both above and below the mean. Okay. Now, if you look at this distribution, right, and I'm not assuming that all of you did this, but we can't make that assumption, right? So if we took 949 and we said, how many values are at or below 949, okay, and then how many values are above 949? And you would have found, if you did that, and I mean, you could also have made a bar graph to look at the shape, right? But if you did that, you would have noticed that 57% of all of the data scores are located above the mean, while 43% of the data in this distribution are above the mean, right? So 57 below, 43 above. But when we look at our estimated percentile, right, we are assuming that we have a 50-50 split. So that means that there's actually a greater percentage of scores that are located in the area we're interested in, right? 57 is extending from the mean across, but there is 7% more information generally on the side of the mean in which we're finding our percentile. Thus why the exact percentile is greater than the estimated one, right? There's simply just more data on that shaded area. So hopefully that kind of helps make sense of the question that was on the activity, and really hits home and kind of helps to further explain the difference between these two types of calculations.